Greetings, we are from Group 5 and today we will present to you about the fusion nuclear energy technology. Nuclear fusion is a reaction in which two or more atomic nuclei are combined to form one or more different atomic nuclei and subatomic particles. The difference in mass between the reactant and product is manifested as either the release or the absorption of the energy. Nuclear fusion is the process that powers active or main sequence stars and other high-magnitude stars where large amounts of energy are released. In other words, nuclear fusion is two lighter nuclei are joined together to make a heavy nucleus while energy is released. Fusion of nuclei lighter than this released energy, while the fusion of heavier nuclei results in the energy retained by the product nucleons, and the resulting reaction is endothermic. Nuclear fusion uses lighter elements such as hydrogen, helium, which are in general more fusible, while the heavier elements such as uranium, thorium, and plutonium are more fissionable.
The most convenient fusion process involves two isotopes of hydrogen, which are deuterium and tritium. This reaction, which is also the simplest to carry out since it takes at least amount of energy input, produces a helium nucleus and neutron, both of which can be used to operate at the reactor and generate electricity. Next is about fusion as a sustainable energy source. Although much remains to be done to reach commercial electrical power, nuclear fusion is one of a very few sustainable options to replace fossil fuels as the world's primary energy source. Fusion energy would be unlimited and deployable wherever in the world due to the abundance of fusion fuel made from water and lithium. As a result, fusion might provide practically limitless energy and supply security at no cost to the environment. In addition, fusion has the potential to be a big baseload source of electricity with no high-level radioactive waste and no carbon footprint. Finally, fusion is an inherently safe process that can be stopped at any moment simply by turning the power off. Fusion power bears the promise of a clean energy production and transmission, proliferation-resistant fuel cycle that doesn't generate high-level radioactive waste, power plants with inherently safe technology features, and lastly, abundant and inexpensive fuels readily available to all nations. Next part is about the challenges of controlled nuclear fusion. The development of commercially feasible fusion power faces significant technological obstacles, the most difficult of which are firstly attaining and maintaining temperatures of over 100 million degrees Celsius while containing the hot fusion plasma within the reactor vessel. Secondly, finding the right material from which to construct the fusion reactor vessel. And lastly, advancing technology for producing the tritium component of fusion fuel from neutrons generated in a running reaction. In a fusion process, the high temperature plasma must be confined for long enough. It is because the fuel nuclei to combine. In the Sun, the pressure caused by the hydrogen fusion is balanced by the inward acting force of gravity to keep the solar core in equilibrium. But this force is far too weak to provide the necessary confinement on the scale of an Earth-based reactor. However, the plasma confinement is never perfect and the instabilities arise, which send plumes of hot plasma into the reactor wall and its lifetime become reduced. There is still ongoing research to better understand about the model and mitigate these instabilities, such as the reactor components must survive long enough before they need to be replaced for the reactor to produce energy on a commercial basis. A further concern is the construction and operation of the large superconducting electromagnets required to create the magnetic fields. These are expensive, heavy, and consume a large amount of energy themselves. They operate only at a very low temperature, which is negative 270 degrees Celsius, just 4 degrees Celsius above absolute zero. But in close proximity to the hot plasma, more than 100 million degrees Celsius, which creates the largest known temperature gradient in the entire universe.
The next challenge is regarding finding the right material from which to construct the fusion reactor vessel. The suitable materials should have the following properties for a reactor to be viable, such as a high melting point and conductivity, and also resilience with respect to damage through exposure to the high energy plasma particles. Other than that, a low propensity to become activated through bombardment by a high-energy neutrons produced by the fusion reaction, is also one of the materials to construct the fusion reaction vessel. A low tendency to absorb tritium is needed as well to reduce the amount available as fuel. The retention of tritium creates radioactive waste which requires special handling when decommissioning the reactor material. Before fusion can occur, a high temperature and stable plasma of deuterium and tritium must be created. The magnetic field driving the plasma particles in a current around the tokamak creates some of these heating through non-fusion collisions. However, to reach the very highest temperatures requires additional heating. This is provided through high-frequency electromagnetic radiation and through neutral beam injection. Neutral beam injection is a high-speed beam of particles which must be uncharged to penetrate the magnetic field. It is fired into the plasma where it transfers its energy through collisions. Alongside the process which heat the plasma, impurities can lead to it cooling through unwanted collisions and the emissions of light. The deuterium and tritium fusion process requires tritium as a component of its fuel. Tritium is a radioactive isotope of hydrogen with a half-life of 12.3 years and does not occur naturally in any significant quantities. However, it can be formed in a nuclear reaction by neutron activation of Li, an isotope of lithium. The proposed approach of this is to surround the reactor with a blanket of lithium that contains material which would slow down and capture some of the neutrons produced by the fusion reaction to breed the tritium fuel. To conclude, making commercially viable fusion power a reality is fraught by serious technological challenges such as the ability to create an environment similar to that of the Sun. This means reaching temperatures exceeding 100 million degrees Celsius and confining the fusion fuel to vessel within the reactor. Additionally, finding the right material to construct the fusion reactor and developing the mechanism that will be used to extract the enormous energy or heat that is emitted are among the other major challenges in the quest to produce electricity from fusion. Harnessing commercially viable fusion power is very challenging, although fusion reactions have been successful during experiments and the technologies are continually evolving to address the challenges.